Hey folks, this is the first in these series of little mini lectures I'm going to post for you guys to view instead of having regular class this week. Rather than doing two big old chunks of an hour and 15 minutes, I thought I'd break it up into smaller pieces, and so I'm looking for probably 4 videos that are about 25 to 30 minutes each. Well, this first, oh wait, before we get started on material, I wanted to show you some stuff about, just where we are in terms of the schedule. Um, the, excuse me one sec. The work we are coming up against soon is the following. We're in this week right here, the 4th, 5th through 8th. So we're going to be trying to get through chapters or sections 3.4 through 4.3 via these little videos. And then we'll have spring break. So that homework isn't due for another, almost 2 weeks. So yeah, that will give you a little bit of a break or a chance to catch up if you want. So let me also point out, I can expand the calendar some, that I've updated everything so that we're good with the schedule of sections we'll be covering up to the very end of the class, with one exception. Chapter 11 has 2 more sections that I haven't scheduled yet because, they'll go right there on the 29th, but they currently don't have the problems assigned, so I have to get that stuff together first, and then those things will appear there. I still don't know why these 2 are grayed out. Maybe it's too far in the future to worry about. I don't know, but in any case, another thing that you want to be aware of is coming up. We had our first exam last week. About 5 weeks out, we'll have our second exam. It should be right in around here between the chapter 6 and chapter 10. So it'll be up through the material we cover in chapter 6. But I will get that on the calendar and give you, a heads up about it and a sample test like we did before, with plenty of time to spare, a couple of weeks at a minimum. Yeah, so that's where we are from here until the end of the term. Yeah, so the stuff we're going to talk about today is complex numbers, and I've gone and moved where I had set the book up to the exact right spot, and then I moved it. Oh well. Here it is, the beginning of the section on complex numbers. So why is this related? Why is this even in the section on polynomials? The thing about complex numbers that they don't really say to us here in the textbook, but I really think the proper way to think about them is that they're the sort of things that come out of the quadratic formula. In particular, if the part, where you have the square root has a negative number under it, then that's when you get a true complex number. But even if it doesn't, if you've, the answer is a real number in that case, which tells you something kind of nice, that the real numbers are contained in the complex numbers. They're just a special case. The way they define the complex numbers here in the book is they're things that look like a plus bi, where a and b are real numbers. Yeah, well, if the b was 0, then it's just an a that's a real number. So yes, real numbers are part of the complex numbers. It would be nice if they had a name for the sort of truly complex numbers, the ones where b is non-zero, but not so far. Well, the very fact that we call these things complex numbers implies that we think of them as numbers, and that means, it ought to be possible to treat them the way we do other numbers. If you turn the page here, example 3.4.1 has us taking some complex numbers, more or less random ones, and trying to add or subtract them, or multiply them, divide them. That is, can we figure out how we do the regular operations with complex numbers? The same things we could do with real numbers should be possible with these. To get a better handle on that, let me pull up my DocCam and we'll try a few of these. So the first operation they had in the book was subtraction. I think we want to maybe do it one notch easier. What if I asked you to add a couple of complex numbers? I've got on mind 3 plus I as a single complex number, and I'm going to add 2 minus 2I to that. How does it work? Actually, the way it works is sort of, how to put this nicely? The way you should always think about these things is as if they were polynomials. So while I'm looking at 3 plus I plus 2 minus 2I, I might think of it as 3 plus x plus 2 minus 2x. Turn the i's into x's. Now, you don't do this really, but in your mind's eye, you think that way. Why? Because that you're very used to the thing that you do in this, guys. You deal with like terms. You put the like terms together. So the 3 and 2, those are both constants, and the x and minus 2x, those are both multiples of x. Those things can be grouped. Well, okay, so let's do that with our actual example. 3 and 2, the real parts of those complex numbers, we add those together and get 5. And then I and minus 2I, those are the imaginary parts of the complex numbers, but what do you get if you add a thing to negative 2 of it? You get minus I. Why don't we return to the example they were doing in the book where we're subtracting? You can actually see the way the answer is collected right here underneath of it. But we're looking at number 1, which is the difference of 1 minus 2I and 3 plus 4I, like that. Well, we just did it for addition. Subtraction is not that much different. 1 minus 3, giving us a negative 2 as the real part. And then the pieces that are imaginary, it's minus 2, minus 4. A total of minus 6, which you can see they've got there in the solution. Now, the next example of an operation with complex numbers they show is right here. That's multiplication. And I think we should probably jump over to the doc cam again and do one of those. Let's see. How about, I don't want to, oh, I know, let's use the same numbers. We'll just take the same numbers, and instead of adding them, we'll multiply them. So we have 3 plus I, and we'll times that by 2 minus 2I. Well, the book talked about distributive property and stuff, but I think this is a FOIL rule scenario. If you're used to working with binomials, treating those things as two polynomials with two terms in them. But I want to suggest that for complex numbers, you just change things up a little bit and talk about Floy rule instead of FOIL. Little first, last, outer, inner. Why? Well, it turns out the first and the last are going to give you the real number parts, and the outer and the inner are going to give you the imaginary parts. So let's see how that turns out in this example. First times first is 3 times 2, you get 6. Last times last is I times negative 2I. Let's just write that for the moment. A times minus 2I. Right. And then, okay, let's finish it out. Outer times outer is negative 6I. And inner times inner is plus 2I. But this piece that I wrote that has an I and another thing that's got an I in it, when you multiply those two bits together, you're going to get an I squared. So there's 2 copies of I in the thing. So in fact, what you've got is negative 2 times I squared. But we have to not forget that I squared is negative 1. So that thing I put a box around is actually a plus 2. A little low. 6 plus 2, and we can combine those two. Well, maybe we should just write it all out first and then we'll combine. Yeah, the real parts combine excuse me, together to give us an 8, and the imaginary parts, well, negative 6, but plus 2, that's negative 4. So there's a product of those things, put into the form, again, of a complex number. So if you adopt my practice and do Floyd, your first times first is always going to be real, but so is the last times last. And I just want to, excuse me, I just want to emphasize that in here, you're using the fact that I squared is equal to -1 every time. That's why it makes sense to do it first and last together to get the real numbers. All right, well, let's transition back to the book. The last, well, not the last, but the next operation they have here is a division with complex numbers. And division with complex numbers relies on a sort of a funny how to say it, a trick that one can apply. So what is the trick? It's called complex conjugation. And basically it means if you, I'm trying to spell at the same time, that's a J, conjugation. Complex conjugation. I'm sorry how that J looks like a G. Oops, my bad. Anyway, it means you take a number like a plus bi, a complex number, and whatever the b is, you replace it with its negative. So you conjugate and you get a minus bi in this case. Of course, if I had a minus bi and I changed the negative b to its negative, we'd come back to a plus bi. So these things are, it's symmetrical, right? If you have one, you can get the conjugate, but the conjugate of the conjugate is back to where you started. So why does that help? Well, check out what happens when you multiply a complex number times its own conjugate. I'm going to do just a simple one, 3 plus twice I. The conjugate of that will be 3 minus twice I. And let's fly it. 3 times 3 is 9. The last times last is, watch out for all this stuff here. There's a minus sign because of the minus in there. And there's the numbers 2 and minus 2. Okay, multiply those together, you get -4. Then there's another minus sign because we've got an I squared in that product of last times last. So all told, that's plus. 9 plus 4. The outer times outer and the inner times inner, interestingly, are exactly the same number except negatives. So outer times outer gives us minus 6i, and inner times inner gives us plus 6i. Now if you think about it, that's always going to happen if you've chosen the numbers this way. See how the outer times outer amongst that pair of things and the inner times inner will be just negatives of one another? So these go away, and it turns out then the complex conjugate times its original is 13 in this case. We can even do complex conjugation sort of in general, and it's sort of nice to see what happens in the general case, because there's an easy formula for the product of a number with its conjugate. So I'm writing the complex number, not an actual number, but one with variables in it. You see that you're going to get first times first is a squared. There's going to be a minus sign from the second thing's minus sign. We'll have b squared, and then there's another minus sign because of the I times I. So this is a squared plus b squared. And the other stuff, abi and minus abi, cancel each other out. So that's it. So it's a kind of a nice reduction. You can look at a complex number and say right away what is the product you get when you multiply by its conjugate. Like if I want to do something different from the one we had up above. How about if we did 5 plus 12i? Yeah, I don't have to do much work to see what's going to happen with that when I know it seems like it's a little bit of work, but it's really not. The answer is going to be 5 times 5, 25, plus 12 times 12, 144. That's 169. So it's quick, right? You don't have to actually FOIL or FOIL or whatever product rule you want to, whatever method you want to use to multiply the complex numbers. You just know in advance. You're just going to need the square of A and the square of B and add them up. So that's complex conjugates. Why is that useful? Let's transition back to this division problem. We want to divide 1 minus 2i by 3 minus 4i. And I need to show you the trick. Hold on 1 second. I said hold on 1 second, and then I paused the recording, so I guess that was not a second even. You had to wait. All right, so let's look at the product they gave us. 1 minus 2, I said product, it's quotient, the division problem they set to us. 3 minus 4i is in the bottom. What I'm going to do to accomplish this division is multiply in the top and the bottom by the same thing. Now the fraction bar serves to group things, but I'm going to be explicit about my parentheses. That same thing is going to be the conjugate of what's in the bottom. So we'll write 3 plus 4i down below. We'll also do 3 plus 4i up above. Cool. The reason for this is that when we multiply the junk in the bottom, it's going to turn into just a real number. In fact, it'll be 9 plus 16. I can see that from the A and the B and the thing. So that's 25. Right? Quickly, we've got the bottom simplified because of it having that shape of a number times its own conjugate. The top, we have a little more work to do, but the bottom is just a divide by 25. First times first is 3. Last times last is negative 8 with an I squared. That's positive 8. Outer times outer is 4i. Inner times inner is minus 6i. So then, combining like terms, we end up with, what's that? 8 and 3 is 11. Minus twice I over 25. Now, at some level, you might think, well, I haven't really accomplished anything because I've still got division here. But dividing by just a single real number distributes. Actually, multiplying by any real number. Multiplying a complex number times a real number, you just multiply the bits. Again, just like you would with a polynomial. So this dividing by 25 can be spread out across the two parts. It's 11 over 25 minus 2 over 25 times I. Real number, other real number times I. That's a plus bi thing. You might want to quibble that it's an a minus bi thing, but if I treat the b as negative 2 over 25, then it's a plus bi. All right, so that's operations with complex numbers. They're really not that bad. The dividing was a little bit of a tough one, but the certainly adding and multiplying aren't too bad. All right, so let's keep rolling through the book here for a little bit. There's this. I always tell people when you're reading a book, you should look for these highlighted things, these stuff that's in boxes, because there's some important junk in there. The important junk in this is, well, twofold. One is getting you used to the idea that we can use a single letter variable to refer to a complex number. Even though it has 2 bits, right, so that an a plus a bi, use a single letter like z to refer to that whole thing, or w. And the first line they've got, oh yeah, and I should mention what the over bars are about. A number with a bar over it means take the complex conjugate. That's just the notation people use for that. Well, this first thing is saying if you conjugate twice, you get back to where you started. Does that make sense? I hope so, because you're turning the imaginary part negative, and then you're turning the imaginary part of that negative. You're back where you started. These next two things say that complex conjugation kind of plays well with both adding and multiplying. So let me just put these into words. The first one says, if you add up the complex conjugates of some complex numbers, it'll be the same as add the two things up together and take the complex conjugate of that. And similar thing with multiplication. This is multiplying the individual conjugates versus taking the product and then conjugating that. Since that works for multiplication, powers are just repeated multiplication. Yeah, it works for powers too. So they're putting these things in here because you use them in a proof later on, but we're going to approach that proof a different way. So I think they're all pretty reasonable things to recognize, and that it is useful in your work of trying to simplify algebraic expressions to know those facts about conjugates. This last thing is kind of an interesting bit. If you've got a real number, then what does that mean? If you're thinking of it as a complex number, but it's actually a real number, that means the a is something, but the b has to be 0. Right? If you think of it as a plus bi, and the I part, the thing multiplying I, is 0, then you're just getting a real number. And if you change the sign of 0, it doesn't do anything. So z's conjugate is z if you've got a real number. But also vice versa. If you find some complex number where if you conjugate it, it doesn't change it, then that must have been a real number. Here's where we're finally seeing them bring in the quadratic formula. See how they've used the quadratic formula to find solutions to some problem. But the real upshot of that is, what kind of numbers did they get out? Well, it did depend on the part under the square root here being a negative, but since it was, we got a complex number with an imaginary part of 2i, or minus 2i. Okay, so why do we care about this stuff? Well, it's a basic thing called the Fundamental Theorem of Algebra, this is only a piece of it. This is the first part of it. But anytime you have any polynomial, it factors over the complex numbers. It may not factor over the reals, but it does factor over the complex numbers. So you can find a 0, and if you can find a 0, you can divide it out and keep going like that. So if you're willing to work with complex numbers, you're able to completely factor every polynomial. I'm not going to talk about the complex factorization theorem. I wanted to pass on to this terminology. I've used it probably more than once just by accident, but it's a big idea. When you have a real polynomial, that is one with real numbers as the coefficients, that's as bad as its factoring can get. You can break it up into linear bits and things that are called irreducible quadratics. You guys saw that in one of the activities where you just made up an irreducible quadratic, something that didn't have a 0 in the real numbers. It does have zeros in the complex numbers, but that's sort of okay because we can pull them out with the quadratic formula. But the thing that's cool is no matter how big the polynomial is, when you factor it down completely, you've got nothing but linear and quadratic terms. There are no higher powers to worry about. Now, because quadratic terms are the things that actually are an impediment from breaking the thing down all the way to linear terms, you get this. I want to prove this by a different route than what they do in the book. If you've got something that's got an irreducible quadratic in its factorization, then when you throw the quadratic formula at it, it's going to break into something like negative b. Well, remember the plus or minus in there? Yeah, so it's going to break into something that involves a complex number and its conjugate, just because that's the way the quadratic formula is built. It has a plus or minus in the middle. And that means the complex roots or complex zeros of a polynomial always come as pairs of conjugates. They instead are using some of the properties of conjugation that we previously wrote down and the stuff in that gray box, and then proven that if z is a 0 of the function of the polynomial, then z bar will also be a 0 of the thing. But I feel like that's a little too far. It really just is a reflection of how the quadratic formula works. So I'm going to say this one more time because we're looking at the thing. The real factorization theorem. Some people call this thing the fundamental theorem of algebra, because it is the most important result in the algebra of polynomials. says if you've got any polynomial function where the real number, the coefficients are real numbers, you can factor it. And when you're done, you will have a product of linear factors corresponding to the real zeros, and there will be these irreducible quadratic factors, which give the non-real or the complex zeros of f. Correspond to them anyway. So I am not going to follow along with example 3.4 here, but you might want to look it through. I just want to note for you that there's an interesting little thing that they're doing. They're using the synthetic division tableau to divide out a zero of this polynomial, and they're starting with thinking a sort of a guess at what a zero might be, 2 plus 2i. Now, this polynomial, x to the fourth plus 64, I mean, if you try to look for its zeros, it doesn't have any at all. It's 64, it's like x to the fourth, but pushed 64 units up in the air. So it has no real zeros at all. And that tells you something, because in light of the factor theorem we just looked at, it's got to break up into two irreducible quadratics. And what are they? Well, we take a guess at one of the zeros, and synthetic division works even if you use complex numbers as the minus r thing. So it comes out 0, meaning the remainder is 0. Rather, it means that it divided evenly into the original polynomial. And so you've proved that x minus 2i is a factor. And then you can keep going. If you think 2 minus 2i is a factor, it ought to be the case that 2 plus 2i is a factor as well. And they divide it out and find it. So I'm going to do like I said and not beat that one to death. Let you look through that yourself. I think really that brings us to the end of where we want to be for this section. It's I forgot to start my timer, so I don't know how long this video is, but it shouldn't be more than about 20 minutes. Anyway, stay tuned. There are going to be a few more of these coming your way. And I'll see you all in 2 weeks. I'm kind of sad to be missing you. All right, bye.